The last topic for Chapter 5 is independence in the multiplication rule. Again, we stop at section 5.3. So we first need to talk about what independent events are. Knowing the outcome of one event does not change the probability of the other. Those are called independent events. That means that if I know what happened in one event, I have no idea what's going on in the other event. So again, knowing the outcome of one event does not change the probability of the other. So they're independent from each other. Dependent events means that knowing the outcome of one event does change the probability of the other. If I know what happened with one event, I automatically know what happened with the other. So these are dependent on each other because knowing one changes the probability of the other. So let's look at some examples because I know this can be a little confusing. It says, does knowing that a coin landed on heads the first flip change the probability that it will land on heads the second time? So let's think about that. If I flip a coin, lands on heads the first time, does that change the probability? That's what we're thinking about. Does that change the probability that it will land on heads the second time? Your gut should be saying no. Every time you flip the coin, you have a fair chance of heads or tails. It has nothing to do with the flip before. So if the answer is no, these events are independent. Knowing the outcome of one does not affect the probability of the other. Let's look at another example. Does knowing that a die landed on 4 the first roll change the probability, and that's what we're focusing on, change the probability of landing on 4 the second time? So again, if I roll the die, whatever it lands on, does that change the chances of it landing on whatever the next time? And the answer is no. So these are independent events. So flipping a coin is independent, rolling a die is independent. Situation 3, does knowing that a clubs was drawn the first time from a deck of cards and not put back, does that change the probability of clubs for the next draw? So the key words here is not put back. If I don't put the card back in the deck, the next time I draw a card, everything has changed in this deck. So at a casino, when they draw cards out of the deck and lay them on the table, every time they draw a card, it's changing what's left in the deck. So the answer to this question would be yes. Knowing that a clubs was drawn the first time from a deck of cards and not put back, that does change the probability of clubs for the next draw. So these events are dependent. There's several movies about playing poker and counting cards and trying to predict what cards are coming up based on what was drawn. We are not getting into all that craziness for this course. That is into conditional probability, which is in the probability standalone course, not in this introductory statistics course. So the real question here is, what does that have to do with probability? Why does it matter if they're independent or dependent? So what we need to focus on is if the events are independent, we can easily calculate various probabilities. So if each time does not affect the next, piece of cake, we can calculate probabilities. If the events are dependent, it is almost impossible, and it's not impossible, but it feels impossible to calculate various probabilities as they are constantly changing depending on what happened previously. This is called conditional probability, which is, again, if you were to take a standalone probability course, you would study conditional probability. It's much more complicated than independent probability. So if you look on your formula sheet, we're studying everything on the left-hand side of Chapter 5. We are not studying anything on the right-hand side because it's about conditional probability, and we don't go there. So for our course, we're only keeping 2 independent events. As you can see here, we're not getting into conditional events. All right. So we're going to focus on the multiplication rule for independent events. Again, it's very important that the events are independent so that this is easy for us to calculate. All right, so if you toss a fair coin twice, sorry, I'm trying to fix the camera here. If you toss a fair coin twice, what is the probability of it landing on heads both times? So the probability of heads the first time and heads the second time. So you have 2 flips. We're going to multiply them together. So you have a 1 out of 2 chance the first time and a 1 out of 2 chance the second time, which gives you a 1 out of 4 chance, or 0.25, that it lands on heads both times. So anytime you want something to occur more than once, both times, all the times, if the events are independent, which for this course they will be, the events are independent, then the multiplication rule applies. The probability of E times the probability of F, which again, for this course, that will generally be true. The probability of E and F, you just multiply them together. And you'll see that here. Same thing is true with a ton of independent events, no matter how many you have, 2, 3, 4, 5, however many you have. If they're independent, you just keep on multiplying however many you have. So if we look at this example at the bottom here, what is the probability of a die landing on 4 3 times in a row? So the probability of it landing on 4, I'm going to put F for 4, is 1 out of 6. So there's 6 possibilities, one of those is 4. If I want it to land on 4 3 times in a row, so the first time, the second time, and the third time, it would be 1/6 times 1/6 times 1/6. This is called repeated multiplication, and a more efficient way to write this is 1/6 to the third power. So using exponents to represent repeated multiplication. So in your calculator, the most efficient way to do this is 1/6 raised, which is the little caret, raised to the third power. In an older calculator, it looks a little bit different. You have to use parentheses here, so you want to do clear all that out. You want to do 1/6 raised, oops, sorry about the glare, to the third power. So on the newer calculators, it looks more like an exponent. On the older calculators, you just have to make sure you have that caret. And either way, you should get the same results. 0.00463. Which is a pretty rare, unusual chance of happening, landing on 4 3 times in a row. And then same idea, what is the probability of it landing on 4 10 times in a row? That would be 1/6 to the 10th power. And that is a super small number. Whoops. 1/6 to the 10th power is a very small number. And I want to take a minute and talk about this little e with the negative, because every now and then you're going to get that as a result. So this is called scientific notation. You might be familiar with it from a previous course. When you see this little e to the -8 or positive, usually in our course it's going to be negative, that means you take the decimal point and you move it back 8 places. So the first move is to get in front of the 1, and then 7 more moves before the decimal point. So this answer is actually 0.00000016538. So again, carefully pay attention to your calculator. If you get that little e to the negative, that means take the decimal point and move it 8 times back, and that means you put 1 less than that number for zeros. So if it's 8, you put 7 zeros. If it's 10, you put 9 zeros. So 1 less number of zeros in front of your number, which for our course is practically 0. It's practically not going to happen. So if you think about that, if I'm rolling a die, it's practically not going to land on 4 10 times in a row. The chances of that are so small that it's probably not going to happen. Just wanted to point out that scientific notation if that ever happens to you. I know some students aren't sure what to do there. On your homework, you'll just put in 0. It's not going to happen. Not impossible, but close. All right. So the last part of section 5.3 is what I call the at least one probability. This combines the complement rule with what we've been studying for the multiplication rule. So it's kind of putting those two rules together. So if you see the phrase at least one, sometimes you'll see at least once. So at least one or at least once used in a problem. Then the complement rule can come in handy. And so we're going to, again, combine the complement rule with the multiplication rule. Now this takes some logical thinking, which your brain can naturally do, so kind of let yourself think about this. This should logically fit into your brain, hopefully. I'm going to explain it a couple different ways, but hopefully this method will click. Just listen carefully and really try to internalize what I'm describing. So to calculate the probability of at least one outcome happening, it's easier to use the complement rule. So think about what at least one means. If I were to say, I hope at least one student passes my course, that means 1 or 2 or 3 or 4 or 5, all the way up to however many students are in my course. So at least one is actually a very long range of outcomes, and it would take a lot of time to think about 1 or 2 or 3 or 4 or 5 all the way up to however many you have. So if we think about the probability of at least one, which is the event we want, equals 1 minus the probability of what we do not want. So it's basically using the complement rule and just switching the e with the e of c. That doesn't matter. It's the same calculation. So it's the complement rule with the e and the e to the c power switched. Same idea. The probability of what we want is 1 minus the probability of what we do not want. So again, this is a version of the complement rule. So the probability of at least one is 1 minus the probability of not at least one. So I want you to think about, what does not at least one really mean? If I said not even one person passed my class, right? If I said not at least one, so I wanted at least one person to pass, and that didn't happen. That means that no one passed. So not at least one, which is a weird phrase, really means none. So if not even one person passed my class, that means nobody passed my class. So this is kind of my take on this calculation. You can remember this phrase, it can help you kind of use the complement rule to answer these questions. So the probability of at least one is 1 minus the probability of none. And that kind of rhymes. If you say it a couple times, it kind of rhymes. The probability of at least one is 1 minus the probability of none. So 1 and none kind of rhyme. Alright, so I'm going to use my own example here. These are not in the textbook. I don't really like the textbook's examples. It's about murder and it's very dark. So I'm going to use a little lighter of an example. And I'm going to do 2 of them. I'm going to work this one with you, and then I strongly encourage you to pause the video and try the second one on your own, using what we learned to kind of help you internalize this. Alright, so this example again is not in the textbook. It says Dr. Pepper advertises that 15% of bottle caps have a winning code under them. So you guys remember, I don't know if they still do that, where you unscrew the cap, you've got a code underneath. And they're saying that 15% of them are winning codes. If you buy a 6-pack of Dr. Pepper, what is the probability of at least one bottle cap code being a winner? So, the way we're going to set this up is with this concept. So the probability of at least one winning cap. So at least one winning cap, that's what we want, equals 1 minus the probability of not at least one winning cap. I know I'm making that a little wordy, but that's the best way to think about it. So what you want is at least one winning cap. And you do 1 minus what you do not want. So you don't want nothing to win, right? If you want at least one winning cap, what you don't want is for them all to be losing caps. So 1 minus the probability of none winning. So 1 minus, we have 6 bottles. So 1, 2, 3, 4, 5, 6. The probability of winning is 15%. So what is the probability of losing or not winning? If you do 100% minus 15, you get 85% or 0.85. So you want to think about what you want is to win, what you do not want is to lose. So if there's a 15% chance of winning, 100 minus 15 is 85% chance of losing. So if none of them are going to win, that means they're all going to lose. This is all lose. So 0.85, 0.85, 0.85. This is again repeated multiplication. Each bottle is independent. More elegant way to write that is 1 minus 0.85 to the 6th power. That's going to give you the probability of at least one winning cap. It's faster than doing 1 or 2 or 3 or 4 or 5 or 6. That would be a nightmare to try to calculate. And we'll see more of that in Chapter 6, why that's so difficult to calculate. So 1 minus 0.85 to the 6th power. It will follow the order of operations for you, and it will spit out the answer directly, 0.6229, which is about a 62% chance that at least one of your caps is going to have a winning code. Alright, at this point I strongly encourage you to pause the video, try this example. Again, it's not in the textbook, but pause the video, try it on your own, then play the video to see how you did. So here's another at least one example. Again, not in your textbook. I really don't like the textbook examples on this one. So think about you're planning a vacation for the summer. Some of you might actually be doing that. You find out that at your destination there's a 30% chance of rain on any given day. What is the probability that it will rain at least one day of your 5-day vacation? Which I recommend always checking. I made the mistake of not checking that once, and it was miserable. So always check what kind of weather patterns you're going to have wherever you're going. So the probability of what we want to know what's the chance of at least one raining day. That's what we're trying to figure out. What we want to see is what's the probability of at least one rainy day. So that's 1 minus the probability of not at least one rainy day. So 1 minus the probability of no rain. 5 days, no rain. So that's 1 minus, there's 5 days. and I don't want it to rain on any of those days. So the probability of rain is 30%. The probability of no rain is 70%. Again, 100% minus 30 is 70%, which is 0.7. So that's 0.7 for each of the 5 days. We can write that a little more elegantly, 1 minus 0.7 to the 5th power. And that will tell us our chance of at least one rainy day, which is 0.83193. So there's about an 83% chance that it's going to rain at least one day out of your 5-day vacation. If that were me, I would not go on that vacation. So really good to practice this at least one rule. This is a most missed question on the test. So just really go over this, make sure it makes sense. There's more examples in your book. They're about murder and such, but still same idea. And then there's a nice summary of all the rules of probability also at the end of section 5.3. And that's all of chapter 5 that we cover for this course.